Okay. Yeah. So non-stoichiometric or Bartholide compounds are the ratio of number of atoms of one kind to other is not exactly whole number ratio implied by that formula basically. So I give you an example. If you consider NaCl, is NaCl 1 mole of NaCl 1 mole of Na plus ions are together with 1 mole of chloride ions. So the stoichiometry is 1 is to 1. But when we see this for iron oxide, the stoichiometry is not exactly 1 is to 1, but it is 0.84 is to 1. It means that Fe2 plus ions are 0.84 moles to 1 mole of oxide ions. So O2 minus is oxide, O minus is peroxide. Okay, so O2 minus is superoxide. So you should be knowing about this oxidation state of oxygen, in which uh, oxygen can have different oxidation state from -2, -1 to +1, like that. So yes, so that was about the non-stoichiometry basically. Okay, so in this is a particular kind of non-stoichiometry in which you understand that iron, that is a cation, is in lower amount than the anion. So basically a metal excess or metal deficient. So you understand that metal is deficient in this metal oxide, as there are less number of cations. Okay, so this was, I think I was discussing the negative ions is absent, means at from the lattice position one of the anion is missing, and that is occupied by a electron. So when this is happening, the formula implied by this is AX 1 minus delta. So what is the thing? So there is a less amount of anions in this metal oxide, and how the electrical neutrality is maintained at side vacant anion side, it is occupied by an electron. And this kind of deficiency leads to deficiency of anion leads to N type of semiconductivity. In N type of semiconductivity, electrons are the charge carriers. Okay, so that so in N type of semiconductivity, electrons are charge carrier. Similarly, this word F center is also used for negative when in a lattice negative ion is absent. This kind of defect caused by when negative ion is absent, and this is because F means Farbe. Okay, that is a German word for color. So Farbe center means there if the number of deficiency of anions are more intense the color will be because of electronic transition basically. And this kind of defects can be also achieved when we heat the salt with its constituent metal vapors. So here if you heat the sodium chloride with sodium vapors and potassium chloride with potassium vapors, then you are going to get this kind of deficiency in the crystal. Okay, but remember, this crystal is electrically neutral, only it is a semiconducting type, because there are, and it is N type because the charge carriers are electrons. Again, you understand, a anion is less, that means a cation will be more. So it is a metal excess kind of defect. An example for this is heated sodium chloride, potassium chloride, lithium hydride, and delta titanium oxide. So this kind of defects are seen in this kind of oxides and salts. So you understand which is oxide, which is salt, and which is hydride here, right? Hydride is lithium hydride. Salt is a, what is a salt? it is a product of acid and base. So here it is a salt, here it is a salt, this is oxide, and this is a hydride. Similarly, a metal can be accessed in an interstitial position. And when there is an excess of metal in the interstitial position, there will be electron at another interstitial position to maintain the electrical neutrality. This kind of defect is also metal excess defect because there is more number of metal cation in that, right? So 1 plus delta, some amount will be more than the anion which is there, and this kind of defect also leads to um, n type of semiconductivity, and where the electrons are the charge carriers, so electrons can move in the lattice, and this will lead to a semiconducting nature. So zinc oxide, cadmium oxide, Cr2O3, Fe2O3, this kind of oxide are usually have this kind of interstitial ion defect, okay, and there is interstitial electron also. Next was if defect can occur when a positive ion is absent. For example, there was a simple lattice in which you see the white solids are cations. I'm audible. I'm there with you, right? Defect, that is uh, metal deficiency. So here what is happening, a cation is missing. A cation is missing, that means a positive charge is missing and a negative charge is more on this lattice. So how the electrical neutrality can be maintained? So if a cation is missing, it can be replaced with another divalent or more than one oxidation state cation actually. So it is here, if A plus is missing from the side, at some position A plus may be A plus 2. Okay. In this case, what is happening is the in this case, there is a deficiency in a cation, a metal deficiency is there, because you see a cation is 1 minus delta X. Okay, and this kind of defect in the lattice is going to give you a p kind of semiconductor, because a hole is been created, and this hole will migrate when you apply a bias voltage, and there is a hole conduction. So because of that, this kind of thing is known as, this type of conduction is known as p type of semiconductors. Okay. Now another thing I want to tell you, that the cation A plus, if it is missing, it is not always that cation A plus 2 will be there. It may be cation maybe B plus 2. Okay, did you get this? Did you get this? For example, uh, in this FeO in ferrous oxide, if there was Fe plus 2 missing from the side, then it is expected that at some position there should be Fe plus 3, right? At some position there should be Fe plus 3. But instead of Fe plus 3, there can be an impurity like chromium plus 3, which can take care of that charge. So actually just one plus one charge was needed to maintain the electrical neutrality of the lattice. So here instead of iron plus 2, it can be chromium plus 2 if there is an introduction of impurity in that. So please remember this kind of multiple choice question or somewhere, you don't get confused that this has been not discussed. Okay, just understand this kind of deficiency may be also there. Okay. So next and last is extra negative ion in a at an interstitial position, and if this kind of defect occurs, then it will be a metal deficient because there will be more of an ion in that. Okay, non-metal will be there, and you understand it will be some 1 plus some delta. Although the formula was ax, it is some amount of x is more, so negative extra interstitial, and this kind of negativity, this kind of defect is also, it's or can be also in this lattice, the electrical neutrality can be maintained by another positive charge being just for a plus, then it should be a plus 2 like that. Okay, there could be another to take care of the positive charge, extra positive extra negative charge, extra positive charge is introduced somewhere in the lattice. But this is not happening because this type of defects are not known, as negative ions are usually large and it would be very difficult to fit them at this interstitial position. And you understand, a negative charge fitting between negative charges is more difficult than the positive charge. Okay, so because of this is negative charge, they are larger in size. Anions are usually larger in size than the cations, so they will not fit in the interstitial position. So this kind of defects are not very common. Okay, that's what I concluded for my last class.